we're going to talk about how to determine whether a molecule is polar overall and what the dipole moment of it would be. And we're going to keep in mind that bonds may be polar, or nonpolar, and molecules may be polar or nonpolar. And just by the fact of having polar bonds will not necessarily dictate that a molecule would be polar as well. So let's do a little review first. If we're looking to determine whether or not something is, or the shape of something, we would need to look at the number of electron clouds or electron domains. And so we look at the central atom, and then we're going to circle the central atom on each of these molecules. And then we're going to look at how many electron clouds they have. So I'm just going to circle them here so we can see them easily. This is not something that you would need to do or it's not something you would even want to do on your papers, but it's going to help us see it right off the bat. So this first molecule, sulfur dihydride, is going to have 4 electron clouds, and they're all circled here in pink, so 4EC for short, and it's only got 2 bonds. And this is where you go back to either using the chart if you haven't memorized them yet, or where you go to your memory, hopefully, to determine what type of bond this is. Anytime you have 4 electron clouds or electron domains, and only 2 of those are bonds, you have a bent shape. We're going to look at the next molecule. The carbon is the central atom, and around that central atom we have 1, 2, 3 electron clouds, or electron domains, and all 3 of them are bonds. Whenever you have 3 electron clouds and 3 bonds, you would have a trigonal planar molecule. And you need to be careful to remember that we have 2 types of trigonal molecules. We have trigonal planar and trigonal pyramid. And so just writing trigonal is not enough. You have to write the other part of it, either planar or pyramidal as well. And then we'll look at our final molecule, methane. The carbon is the central atom. We've got 1, 2, 3, 4 electron clouds on it. All 4 of those are bonds, and this is a tetrahedral shape. So let's take a look now at the bonds themselves. So we would look at our electronegativity chart. If you have that handy, you can look back at each of these molecules to determine, or each of these atoms to determine whether each bond would be polar or not, and we see that sulfur is more electronegative than hydrogen. If sulfur is more electronegative than hydrogen, it is going to pull the shared electrons towards it more, and so it would be a partially negative charge, and that would leave the hydrogen with a partially positive charge. We're going to do the same thing here, partial negative, partial positive, so this would be a polar bond, and this would be a polar bond. Let's look at the next molecule. Carbon is slightly more electronegative than hydrogen, and so it would have a partial negative charge. The hydrogen would be partially positive. Same thing on this bond, partial negative for carbon because it is more electronegative than hydrogen, which would have a partial positive charge. Then if we look at oxygen, which I'm just noticing now is missing its unbonded pairs. I was getting too excited in my drawing before. Get back to this. Oxygen is much more electronegative than carbon, so it is going to be a partial negative. Carbon would be a partial positive in this bond. So we've got those polar bonds for each of those. And we said in the last molecule that carbon's more electronegative than hydrogen, so carbon's going to be a partially negative, hydrogen's going to be a partially positive. We're going to go through all of these bonds because they're all the same bond configurations, carbon versus hydrogen. And so we get a polar bond, polar bond, polar bond, polar bond. Now we need to determine, we've already determined bonds that are polar or not. We need to determine if the molecules are going to be polar overall or not. And when we do determine their polarity overall, what is the effective dipole? And so we see, I'm going to use highlighter again for this, we see that on this end of the molecule, I have a bunch of partially positive stuff. And on this end of the molecule, not only do I have the partially negative sulfur, but I've got unbonded electron clouds, which are definitely negative because of those electrons. And so my effective dipole, I would be positive on this end, and I would be negative going on that end. And then we'll do the same thing on our next one. Again, you wouldn't need to circle these like I didn't need to circle the electron clouds. I'm just going through, hopefully making it more visible for you. The partial positives of the hydrogens and the really negatives of the oxygen and the carbon compared to the hydrogens means that we are going to have a partially positive on this end and a partially or more negative on that end. So that's my effective dipole. I'm positive on this end, negative there, and there. So those two are both definitely polar molecules. So if we're looking at the intermolecular forces, if I have a whole container of H2S and I'm trying to figure out the intermolecular force that is interacting between individual molecules of H2S, so not the bonds, but the intermolecular forces, I would say, well, I've got a polar molecule. And I do have hydrogens in here, but the hydrogens would have to be bonded to a fluorine, an oxygen, or a nitrogen, and it's not here. So this would have as its intermolecular forces dipole, dipole. And I've got my, in this molecule, I've got electronegativities between all of my bonds. Some are going to be more electronegativity differences than others, but there's going to be those differences. It's polar overall, but there's no fluorine, oxygen, or nitrogen bonded directly to a hydrogen. I have an oxygen, but it's not bonded to a hydrogen, and so this one would also be dipole, dipole. And finally, my last one, I've got a net direction of, this is going to get messy. It looks like I've got, with this polar bond, that I've got a dipole going that way, and a dipole going that way, and a dipole going this way, and a dipole going this way. But they're all the same atom attached to the central atom, which means that the electronegativity difference is going off exactly the same amount in each direction, which means the polar bonds cancel out, and we get a non-polar molecule. And since it is a non-polar molecule, the only intermolecular force that it undergoes is London dispersion, which are those temporary induced dipole moments where electron clouds coming into contact with other electron clouds are going to move and shift and cause those moments where they interact with one another and go together as much as possible. So that is a quick and easy way to think of the difference between bonds can be polar, but that their molecules may or may not be polar. So we've got polar bonds and a polar molecule, polar bonds and a polar molecule, polar bonds but a non-polar molecule.